Hello, and welcome to some notes that I prepared for you regarding the first law of thermodynamics for a closed system. And I want to illustrate what a powerful problem-solving tool the first law is, particularly as you're working through your homework, quiz, and test problems in this class. So let's go ahead and get started. Okay, want to introduce some ideas about the first law that you were introduced to in chapter 2, and these set of notes will apply to closed systems. And here's the tried and true, familiar, very short statement of the first law of thermodynamics. And so here's what we'll cover. A quick reminder in your head of can you think right now off the top of your head, what's the difference between a closed system and an open system? How are they similar and different? Then we'll quickly mention the continuity equation or conservation of mass for a closed system. And then most of this work is going to be associated with stating the first law of thermodynamics and then talking about how to determine the various terms that are mentioned in the first law. Okay, so very, very quick reminder. I bet you that everybody is familiar with this, but let's just be sure we're on the same footing. A closed system in thermo. Well, the classic example of a closed system would be the gas that's contained within a piston and cylinder. But recognize that the key point about a closed system is that the mass is fixed within the control surface, where we started with a sketch, drawn a little dashed line. That's our control surface. And so the mass is fixed. What I've shown here on my sketch is we start at state 1, we end up at state 2. So we're undergoing a process 1 to 2. Now that's different than an open system, isn't it? So in an open system, I've had to draw just sort of a cloud, because in an open system, you have mass flowing into and or out of this control surface. So that's really the big difference. And this cloud, the cloud can get bigger or smaller. The mass of this control volume can change, but certainly one of the key effects is that we have mass flowing into and out of this control surface. Now, notice the similarities. We have heat transfer in on our closed system and work coming out of our closed system, whereas in an open system, we have a heat transfer rate, Q dot, and an output power, W dot, coming out of our open system. So anyway, let's be sure that we fully understand the difference between an open system and a closed system. And this set of notes is going to apply to a closed system. Okay. We're going to restrict our example to a closed system that's undergoing a process from 1 to 2, or state 1 to state 2. So we're going to just try to keep it simple, but you know how to make things general. We're going to go from a simple, specific situation, and you have the ability to think in general situations. So we're going to try to keep it simple here. A quick look at the continuity equation for a closed system, also called conservation of mass. And in a sentence, the mass of the closed system, what's contained in this piston and cylinder example, is constant. The mass is constant from start to end of the process, 1 to 2. And so a way to state the continuity equation is M equals M1, the initial mass, and that equals M2, the final mass. And I've showed this little cartoon as well for you. This is your best formula sheet. Is your brain is the best formula sheet. It's a lot better than plopping down this kind of very simple formula on a sheet, M equals M1 equals M2. You've probably got this in your head. Now we're going to move on to the crux of this set of notes, the statement of the first law of thermodynamics, also called the conservation of energy. And here it is in its simple form. Qn minus W out equals delta E. Okay, and you might say, wait a minute, that's not the way I remember it from reading my textbook. So let's look at that a little bit. Okay, it is different looking, isn't it? But mathematically identical. So little screenshot from your section 2.5. So the first law for closed system was introduced to you in chapter 2. And you're beyond that now. Many of you have gotten near the end of chapter 3. Okay, but chapter 2, it says E2 minus E1, that's delta E equals Q minus W. All right. Now, let me drop down here and make a mention that your textbook just says Q and just says W. I got to tell you that when I was learning this and my professors drilled into my head, and I still do it to this day, instead of just writing Q, I write Q sub N, Qn. And instead of just writing W, I write W out. That keeps me as an engineer straight to remind me the sign, S-I-G-N, of heat transfer and work, okay? And I never write Q out, and I never write W in, okay? So if work is done on the closed system, I write W out as less than 0. If heat is rejected from the system, Q is leaving the system, I write Q in is less than 0. That just helps keep me straight in my problem solving. So that's up to you to decide of how you'll move forward personally as an engineer. All right. Another thing, notice here how my practice of writing the first law is a little bit reversed than the textbook. I start with Qn minus W out on the left side, and I deal with these energy changes on the right side. Okay, and so this is the way I would recommend. This has worked for me. And so consider, it's all up to you, consider this may be working for you. But you see that mathematically, this statement of the first law for a closed system is identical to your textbook. Here we go. So you should commit this to memory. Qn minus work out equals, well, delta capital E, like the textbook. Well, what's delta capital E made up of? It's made of delta U, change in internal energy, plus delta Ke, change in kinetic energy, plus delta Pe, change in potential energy, and in fact, change in other energies such as surface tension energy, magnetic energy, which we deal with very, very little, if at all, in this class. Okay, now that's what I suggest you commit that to your memory. Forget the formula sheet stuff. That's fine to write this on a formula sheet, but do not use the formula sheet as a crutch for you to not be learning the first law for a closed system. Very important. Please commit this to memory. It will pay off for you in quizzes, tests, and the exam. Next line. Notice here, I'm gonna give you a little more detail. What's delta U? It's U2 minus U1. It's capital U at state 2 minus capital U at state 1. That's the internal energy, units like kilojoules. All right. Next line, Qn minus W out equals M times little U2 minus little U1. Well, little U2, little U1, that is the specific internal energy. Kilojoules per kilogram times mass, kilograms, okay? The kinetic energy term, probably remember that from physics in high school. The change in kinetic energy is 1/2 mv squared, v2 squared minus v1 squared. That's an expression of the change in kinetic energy of the closed system. And then, again, I'd say high school physics, the change in potential energy, mg, or the weight of the closed system, mg, times the vertical position relative to the ground, z2 minus z1, vertical position relative to the ground. Okay, so that's maybe not need to memorize, but be able to quickly generate this expression of the first law. Now, in terms of homework solutions, what if you divide this line by m, the mass of the closed system? You end up with little q in minus little w out, units, kilojoules per kilogram, equals specific internal energy change plus kinetic energy change plus potential energy change, all in kilojoules per kilogram or foot-pounds force per pound mass or BTUs per pound. So all these statements for a closed system are identical. So I suggest you memorize the top one, the most important one, and then be able to derive all the rest. I think there's some value in your studying and understanding the nature about the terms in the first law of thermodynamics for a closed system. Let's look at the left-hand side. Q in minus W out. These would be classified as boundary phenomena. So in other words, those are energy transfer terms that occur at the control surface, that dashed line, control surface boundary. Okay, that's why I put it on the left-hand side. That's why my professors led me to this approach. Okay, notice here, we covered this in chapter 2, heat and work covered in chapter 2. Okay, equals change in internal energy, delta U, or M times little u2 minus little u1. That's what you're doing in chapter 3. So throughout chapter 3, you're figuring out, your professor, your instructor is showing you how to evaluate u2 minus u1, delta U, chapter 3. Kinetic energy change. Well, that was covered in chapter 2. You refresh your memory of the reading. Kinetic energy change, potential energy change, also introduced in chapter 2. So you take just a couple of minutes to think about the first law, and we're putting things together. We're putting chapter 2 and chapter 3 together, and the first law is doing that, putting things together. Okay, now this is a little bit of a one-off slide and has to do with as you're working through your homework problems, isn't it common, have you noticed, what's being asked for is what's the work per kilogram of mass, or what's the heat transfer per kilogram of mass? And that can be very confusing because the way you're learning the first law, Q in minus W out equals delta capital U, you got to remember that, oh, it's a little bit of a trick where we have little w is capital W divided by M. Work per kilogram of mass, kilojoules per kilogram. Same thing on heat transfer. Little q in equals capital Q in kilojoules per kilogram of the closed system. Nice thing about that is for a closed system, the mass is constant. Okay. I hope that helps. I hope you understand maybe a little better about what's going on in these homework problems and the way they ask the questions. Okay, now that's essentially my set of notes on the first law, but I want to spend a little more time talking. Let's dissect piece by piece by piece. How do you calculate these things in the first law? That's really some part of the beauty of using the first law. It guides you into getting an overall solution, but you have to be able to pick it apart and calculate or determine things piece by piece by piece. So let's look at W out first. The devil's in the details. Gee, some great questions have come in live on Zoom and also by email. Well, I don't know where to start. What would I do? It asked for W out. I don't know what to do. Okay, let's look at that. You're going to want to ask, it's a little bit like a decision tree on determining W out. And the first question you answer yourself is this process that's in the homework problem or the test problem or the quiz problem, is it a quasi-equilibrium process? Yes or no? Okay, so If yes, so an example of yes, quasi-equilibrium would be the tried and true piston and cylinder undergoing a process that is friction-free and it's going sort of slowly so that at all points from on the process path from 1 to 2, every single state is in a state of equilibrium. In other words, things are moving slowly and without friction. So when the answer is yes, I've got a quasi-equilibrium process, immediately you go to the thought, I've got my fundamental is W out equals the integral of P dV. W out is integral P dV. Now, there may be some simplifications, right? So once you draw your sketch, pressure might be constant. Well, then the integral becomes easy. Or pressure is some function of volume. Then I got to do a little integral. And then also remind yourself, if I'm looking for W out in kilojoules, that's equivalent to the integral of P d capital V is identical to M integral of P d little v. Your units work out right. Study on that. Remember the definition of specific volume, capital V divided by M. Okay. What happens if your process is not quasi-equilibrium process? So now at this point, a classic homework problem that I think every section has had is the infamous rigid vessel where there's a propeller or a paddle wheel spinning around inside the vessel, and due to friction of the paddle wheel and the gas or liquid in the vessel, it's doing work on the material. Well, friction is what is the way that the paddle wheel is doing work on the system. So this is a good example of a non-quasi-equilibrium process. You say, well, how do I get a number for that then? The answer is that for these types of problems, inevitably, you have to look for keywords in the problem statement to see if there's enough information, such as the paddle wheel's operating with so much power over a certain time period. Power times time equals work. Okay, so that would be, for this example, that would be a way to determine the work. So you got to look for keywords in each specific problem statement when your process is not quasi-equilibrium. Okay, now we're going to switch over to the other side of the first law equation and want to give you some details about how do I numerically determine delta U, the change in internal energy, delta U. Okay. Step 0, read the problem and identify the substance. Well, here's a reminder before we get into that. Identifying the substance, delta U also equals the mass times delta little u, or the mass times U2 minus U1. Some good questions have come in about that. A little confusion about what's delta U. What's the difference between capital U and little u? I hope this visual gives you a reminder and an understanding of these differences. Okay, next is another decision tree. Determine delta U. And the question you have to ask yourself as an engineer is, what is the substance contained in the closed system? Okay, so I've got 3 basic categories of substances that you will encounter in this class. Okay, 3 categories of substances. First would be a phase change substance. Examples: H2O, water and or steam. Those words, water and steam, that's H2O. Refrigerant, R134A, R22. Those are refrigerants we commonly found in engineering. Ammonia, NH3. That can change phases. Propane, C3H8. I hope you've watched my propane videos. So those would be classified as substances that can change phases. They can go from liquid to a mixture of liquid and vapor. They can go to saturated vapor, They can become a superheated vapor, all of those substances. Okay, let's continue the decision tree. So you say, I recognize in my word problem that's a phase change substance. I'll write that down. Closed system, phase change substance. Is the substance a liquid or is it something else? Now you got to make a decision here of it's either a compressed liquid or a saturated liquid. More on that in a minute, okay? Or something else. Well, the something else for a phase change substance could be a saturated mixture of vapor and liquid. It could be a saturated vapor. You couldn't see it, but you know it's there. Or a superheated vapor. You definitely can't see it, okay? It's heated beyond being a saturated vapor. More on that in a second. Okay, so that's first category, a phase change substance. The next category of substances, the system is comprised of a commonly recognized ideal gas. And commonly recognized ideal gases are substances like air, mixture of nitrogen and oxygen, nitrogen, oxygen, CO2, carbon dioxide, argon, hydrogen, and on and on and on, things that you recognize in your mind as a gas. Okay. Well, the way you're going to get delta U, U2 minus U1, that's what we're looking for. What's U2 minus U1? You're going to use ideal gas property fundamentals. More on that in a second. Third category of substances would be a solid. Okay. Substances like copper, bricks, concrete, steel, and on and on and on. Okay. For that type of substance, you're going to use an incompressible substance model, fundamentals associated with that. So what I want to do now is step you through category 1, category 2, and category 3, because on all these problems, you're seeking to find U2 minus U1. What's delta U? All right, so my first category, let's say you have a phase change substance and you've done the hard work to determine that the substance is either saturated or superheated, one or the other of those. Okay, so here's our situations. You could have a saturated liquid, couldn't you? Water boiling point. We're going to go to the next slide that's going to give you a visual of this, but think in your mind before we go there. On a PV diagram, where would saturated liquid be? On a PV diagram, where would a saturated two-phase mixture be? A mixture of saturated liquid, saturated vapor. Where would pure saturated vapor be? And we call that steam. We call that steam, okay? Or for H2O, okay? Superheated vapor, where would that be on the PV diagram? And we call that superheated steam for H2O, okay? So the question is, if you have any of those phase situations, you're going to look up U2 and U1 from the appropriate property table. Now, I've given you little screenshots of these appropriate property tables. Well, do I use a temperature table? Do I use a pressure table? Or do I use a superheated vapor table? Okay. I think the next slide is going to reveal that. I think we're headed there, I hope. Here we go. I've drawn a PV diagram for you that, boy, should be really familiar to you by now. Pressure on the Y, specific volume on the X, vapor dome. And as a review, if your state lies on this part of the dome, you're a saturated liquid. If your state lies on this part of the dome, you're a saturated vapor. If your phase lies under the dome, you're a saturated two-phase mixture, and quality comes into play, or you're at a superheated vapor if you're to the right of the vapor dome. To the left of the vapor dome, compressed liquid, that's coming up in a minute. But let's say you're either saturated liquid or a saturated two-phase mixture or a saturated vapor or a superheated vapor. What do you do? Well, this tries to give you a visual of what you do. If you're a superheated vapor, you go to the superheated vapor tables, whether it's water, refrigerant, or propane. okay? And you're going to look up U value. So for example, here's U, my little cursor here. Here's U values that are tabulated for a bunch of different pressures and temperatures. If you're on the dome or under the dome, depending on your specific problem, you're going to use either of the temperature table or pressure table, depending on what's easiest for you. And you will look up, here's internal energy, right here. See me wiggling my cursor. Internal energy as a function of pressure and or temperature on or under the dome. Okay, the next, we're still in category 1 where we have a phase change substance, but you have determined that your phase of the phase change substance is compressed liquid. You're to the left of the vapor dome. What do you do to get U values for that? You need to read section 310 in your textbook. You need to, here's the conclusion. In engineering, compressed liquids are modeled as nearly incompressible substances, or in other words, V equals constant, specific volume equals constant. That also means density equals constant. Now, so for these compressed liquids, it means that you're going to evaluate U at the temperature of the compressed liquid substance. Evaluate U at the temperature, not the pressure, at the temperature of the compressed liquid substance. I think I've got another illustration here. So for example, you've got a homework problem or a test problem or a quiz problem, and you've got the temperature of that, let's say H2O is 90 degrees C. This is an H2O example, okay? What's the internal energy for water, for compressed liquid water at 90 degrees C? This is the point where you go to the temperature table and you look up U sub F. That's the internal energy of the saturated liquid, U sub F, at the temperature of the liquid, 90 degrees C. And so numerically for this example, U, if this is U1, U would be U sub F at 90 degrees C, or 376.85 kilojoules per kilogram. Okay, that's important. I hope that this is helping you understand, how do I get U values when I'm faced with a problem involving the first law? Okay, now we're going to switch gears to category 2 of substances. You have a substance in your homework problem or test problem that is an ideal gas. You commonly recognize it. So you commonly recognize ideal gases in your experience, your life: air, nitrogen, oxygen, carbon dioxide, argon, hydrogen. You recognize all these things as ideal gases in your mind. Oops, it looks like I didn't do and you need to find U2 minus U1. That's your job. So you say, well, what's U2 and what's U1? The neat thing about ideal gases is that in many cases, we have a fundamental relationship for any ideal gas. For any ideal gas, delta U, which is U sub 2 minus U sub 1, equals the integral of CV dt. That's the specific heat C sub V. Specific heat C sub V. The integral from 1 to 2 of CV dt. Now, you need to know some more details about the nature of your ideal gas in the problem. Okay. And I'm going to address these one by one. So you need to know more that I can't answer right here. Could CV be considered a constant value? If it is, if CV is not a formula, if it's a constant value, like 0.2 kilojoules per kilogram, you can pull it out of the integral. If it's a constant number, you pull it out of the integral. So if CV is a constant value, then U2 minus U1 is simply CV times T2 minus T1. Delta U is CV delta T, as long as CV is a constant value. Okay, next thing. Is CV known to be variable? A variable can't treat it as constant, but property values for U are tabulated. And you're going to be able to find these tables in the back of your book. There are air tables, CO2, nitrogen, and carbon monoxide tables, property tables in the back of your book. So if you're directed that the ideal gas has variable specific heat, you need to go use those tables. And then finally, if you have a formula for C sub V as a function of temperature, then you have the ability to perform this integral, the mathematics of performing the integral. So if CV is a known variable function of T, like alpha T squared plus beta T cubed plus gamma T to the fourth, then you can perform this integral. In your homework problems, the top two categories are by far and away the way you will be solving problems in this class. You're going to treat CV as either a constant number, or you will be looking up values for U in property tables. Now, so this is a whole new category, I want to be sure I'm still recording. I'm goofing around with my Zoom menu. Learn more about ideal gas properties and when should CV be treated as a constant, when do I use tables, and when do I do that mathematical integration. I've got Ideal Gas 03 is a video that I prepared for you to give you more information on that rather than covering that right now. So I strongly recommend you, let's say, download the static slides for here and then click on these links for more information on determining delta U for an ideal gas. Okay, finally, the third category of substances that we've got engineering problem solving with, and that would be solids. Solids, copper, a block of copper, a brick, concrete, steel, and on and on and on. So you've got to go back to read your textbook, section 3.10.2, to get a fuller understanding of how to handle internal energy changes for solids. And so, of course, you're going to read your textbook and see big conclusion. U is a function of temperature only. The internal energy is a function of temperature only. And it turns out that for incompressible solids, incompressible substances, the specific heat C is identical to C sub P and identical to C sub V. That is different than an ideal gas. Okay? But it's a neat way to determine internal energy changes for solid substances. Here it is right here. Delta U is U2 minus U1, and that's simply going to be equal to specific heat, C, times T2 minus T1. And here's how would you get the specific heat for brick, for copper, for concrete? You go to table A19. It's a straight lookup. So if your material is steel, then you would look up the specific heat. And here in the table, it says C sub P, but recognize that for solids, C sub P equals C sub V equals C, specific heat. So there you go. That's the way you determine the change in internal energy for a solid. Okay, so that covers how do you get U2 minus U1 in the first law. So the last thing we have to cover in our statement of the first law for a closed system is how do you determine QN, heat transfer into the system? Okay. So, wow, I don't have any recipe related things for heat transfer, do I? So I've got a little paragraph and it says, so far in this class, when you're asked to find the heat transfer in a problem, in most cases, except for a couple, in most cases, this is where you're going to write down the first law and you're going to use the first law to solve for QN. That's the trick. Recognize, oh, I'm asked for the heat transfer. I'd better write the first law. And that's why I just got done spending a lot of time talking about how would you get this number? How would you get W out? How would you get change in internal energy? I haven't talked a lot, but you've worked enough problems in chapter 2 to get the change in kinetic energy, change in potential energy, if any. This is where your brain would go and write this down. You don't need a formula sheet. You shouldn't need a formula sheet to write this down. And so by far and away, when you have homework problems, test problems, quiz problems, when you're asked to find the heat transfer, that's a signal. I need to write down the first law, and I need to determine the numerical values for all these other terms. Okay, we've reached the end of my tips. So let's recap. Let's recap what we covered here. Refresh your memory on the difference between an open system and a closed system. So far, this set of notes only associated with closed system. The continuity equation for a closed system, very simple. The mass is constant. M equals M1 equals M2. And then finally, the first law of thermodynamics for a closed system, Qn minus the work out equals delta E. And that delta E is made up of delta U, delta kinetic energy, delta potential energy. So look, this is your best formula sheet. Your brain is your best formula sheet. Okay. It's great for you to spend some time. If you're allowed to create a formula sheet, that's great. Spend a little time creating a good one that works for you. But recognize that you've got to have most of this stuff up in your head rather than depending on a formula sheet to win the day. Okay. One last idea. This is one of my favorite thermodynamic professors drilled this into our heads, and wow, did it pay off for us. When you get stuck on a thermal problem, you've read the problem, you got a little ways on it, you got your sketch, but then you get stuck. I don't know what to do. I'm stuck. By far and away, if you write down the first law of thermodynamics, you write it down on your paper and study on it, but many, many times you start looking at that, and very often it gives you ideas on how to keep moving ahead. Do I need to get work first? Do I need to get change in internal energy first? Do I have a path forward to find those things? It's simply amazing. If you try this out and try writing down the first law when you're stuck, it's amazing how you will get yourself out of being stuck and get back into moving ahead once again. I hope that helps. Now, let's see. I'm back at it. I hope that helps. And don't hesitate to look at that ideal gas video. And please keep up with your homework, and that's going to prepare you well to take quizzes and tests and perform well in this class. All right. Hope to see you again soon.